Hello class, Professor Anderson here. Let's say we want to calculate the electric field of a line charge using Gauss's law. So first off, what does a line charge look like? Well, it's quite simply a line of charge. Okay? We usually denote the charge on it by a positive lambda, where this thing is charge per unit length. Okay, so it's some sort of charge density, but it's in terms of linear length. Okay, so just imagine you have a whole bunch of positive charges on that thing, and those positive charges are now going to create an electric field. Well, what does the electric field around it look like? By symmetry, we could say that the electric field must be pointing out in this direction. Okay. But if this is a positive charge, of course, it's going away from all the positive charges everywhere. And now you might ask yourself, why is it going perfectly radially outward from this line charge? How come it's not pointing to the right or the left? And the answer is a little bit subtle. It has to be an infinitely long line of charge. Okay? If it is an infinitely long line of charge, then any region of that plus lambda will have a mirror image of another plus lambda over on the other side. And therefore, if I'm calculating the E field right here at this point, what would I get? I would get a little component going that way. I would get a little component going that way. And those two would add up to get me something perfectly vertical. Okay? So this is the idea with this infinitely long line charge. By symmetry, everything has to be radially outwards. It can't be pointing to the right or to the left. It has to be radially outwards. Okay, so that's good because it's going to simplify our problem quite a bit. And let's see how that works. Remember, when you have your picture and you write down Gauss's law, integral E dot dA equals Q enclosed over epsilon naught, the next thing you want to do is draw a picture of the surface that you're looking at. So let's try blue. What would our surface look like? Remember, you want to draw a surface that takes advantage of the symmetry. This thing doesn't have spherical symmetry anymore because it's not a point charge. It has to have cylindrical symmetry. If I draw a cylinder around this thing, the E field lines are poking everywhere through the sleeve of that cylinder. Here's the top of it right here. Okay. Let's draw it sort of the way we drew the last one, where we had dashed lines for the E fields. So if I dash this one out, that means it's internal inside this can. And it's poking out, and so we'll put a little hole right there where it comes out of the cylinder. The E field lines are coming out radially. What about dA for this particular surface? Well, dA is going to look like this. It's a little chunk of this can, and the dA is also radially outward from the center. So E and dA are in the exact same direction. Almost there. Right? We're almost there, except we have to worry about the closed surface. Right? This is an integral over the entire closed surface, and so we have to worry about the end caps. The end caps will have a dA that is pointing in that direction. And over here, it will be pointing in that direction. And those are orthogonal to the electric field, and so we're going to see that they don't, in fact, contribute to our integral. So what does the integral become? We have two now integrals. We have to integrate over the sleeve of E dot dA. And sleeve just means this portion of the can. But we have to also add the end caps and that's what the left side of this thing becomes. Everything on the same right side, Q enclosed over epsilon naught. All right, this is looking pretty good, right? Integral of E dot dA over the sleeve. How do we do with that? How do we deal with that? Well, it is E dA cosine of the angle between E and dA at the sleeve, which is 0 degrees, right? They are parallel, and so those two little vectors are in the same direction, therefore phi is 0 degrees, and so that's going to cancel out real nicely. What about this part right here? E is radially outward, but D is in this direction along the line of the charge, and so we're going to get cosine of 90 degrees. That one's going to go away entirely. And then all of this is still equal to Q enclosed over epsilon naught. All right, this one becomes integral of E dA. And let's just be clear that we're talking about integral over the sleeve now. This one becomes 0 because cosine of 90 degrees is 0. It's all equal to Q enclosed over epsilon naught. So let's deal with this and then we'll worry about Q enclosed. E is a constant. If we are a fixed distance everywhere from that surface, and we call that distance S, then the magnitude of E has to be the same everywhere around that can, right? By symmetry, it has to have the same value. So E comes right out of the integral. E times the integral of dA over that sleeve. All right. But we know that the area of the sleeve is very defined. It's 2 pi s times how long the sleeve is. So let's just give the sleeve a length, L. What is the area of that sleeve? It is 2 pi s times L. All right, once around on that circle, and then move that circle this distance L, and that's the area. All of that has to be equal to Q enclosed over epsilon naught. But Q enclosed is related to this lambda, of course, because this was charge per unit length. So how much total charge is in there? It is just lambda times how long the wire is, L. And then we're still dividing by epsilon naught. And now this is really cool, right? Because the L's cancel out. And look what we get. We get E is equal to 1 over 2 pi epsilon naught times lambda over S. Again, Gauss's law gets you a scalar quantity. It gets you a magnitude of E. It doesn't tell you the direction. For the direction, you have to go back to the symmetry of the problem that we started with. And so now we can write down the final result. What is E in terms of a vector field? It is 1 over 2 pi epsilon naught lambda over S, and it's in the radial direction, S hat. Okay, this is the electric field of a line charge if its charge density is lambda. All right, hopefully that's clear. Cheers.